Hi there. My name is David Weitz, and in this talk, I would like to tell you about joint work with Bernhard Haeupler from CMU and Goran Zuzic from ETH, titled Network Coding Gaps for Completion Times of Multiple Unicasts. Let's start with some motivation. Consider your favorite communication network, the internet, which is simply a number of computers all interconnected by a sequence of routers. And in this network, consider the most basic communication problem, point-to-point communication. For example, the Fox PC chair might want to send me an email reminder that this video recording is due. Now, this simple communication problem is referred to in the literature as a unicast session, where uni refers to the fact that there's a unique sender and a unique receiver, and cast is an allusion to broadcast. Okay, simple enough problem. Let's simplify things further by abstracting away all these pretty pictures. In that case, what we're left with is an undirected graph with two distinguished nodes. And what we'd like to do is find a path between the sender and the receiver along which to send this message. Now, since this is a time-sensitive message, we are interested in the fastest possible solution, which in our context means a shorter path, the shortest possible path. Okay, so a single unicast session just corresponds to point-to-point shortest path. Simple enough. Let's up the stakes and try and solve two unicasts in tandem. So now we have the blue pair and the red pair. Now, if again we look for a shortest path between the senders and receivers, we run into a problem, namely bandwidth limitations. So this particular indicated edge, which is common to both red and blue path, has a bandwidth restriction of no more than a certain amount of information per second. And so what we find is that trying to solve multiple unicasts in parallel might have to, might require some other ideas. Okay, so the question here is, how do we perform multiple unicasts in parallel? So to be a bit more formal, let's formalize the model. So in this talk, the inputs will consist of k unicast instances, which are made of an undirected graph. This is the communication network, and k source sync pairs. These correspond to the k unicast sessions. So in the previous slide, we had k equals 2, so 2 unicast sessions. Here we have k equals 3, and so on and so forth. And if it's not clear by this point, k, the number of source sync pairs, will be an important parameter, so please remember it. Okay, so this is the input. What's the output? We'd like to send information from every source to its sink. So what we want is a communication protocol, which allows us to solve the following problem. Initially, all the SIs will have a 1-bit message XI. And in each round, and the communication will take place over discrete time steps, which we'll refer to as rounds. In each of these rounds, each node will be allowed to send a 1-bit message along each of its edges. And this will take 1 round to cross the edge. So pictorially, such a protocol for the 3 unicast instance on the right might look as follows. In the first round, we'll have all these messages sent along the first edge of the shortest path. Second step will do the same. And then for round 3, you notice that we run into our congestion issue. We're only allowed to send 1 message per round. So what T3 is going to do is it's only going to send, say, X2, and it's going to remember X1 to send later. So by round 4, X2 has already cleared this link. And so X1 can be sent along this edge. By round 5, T1 will have received its message. Okay, so how do we measure such protocols? So the time it took the blue message to reach the blue destination is the completion time for the blue pair. And what we'd like to do in this talk is minimize the time until the latest of these messages arrive at its destination. And we'll refer to this as the protocol's time or completion time. Okay, so we're clear about the input, output, and objective. Now let's be a bit careful about what we mean by protocols. So in the previous slide, what we saw was an example of a routing protocol, which only stores and forwards messages it received. And this can be thought of some kind of multi-commodity flow, where we have flows that correspond to each of these messages, as though they were physical packets, and we're sending them along maybe a road network. But as it turns out, as pointed out in a highly influential work in the early 2000s by Alsved et al., information is not a physical commodity, and there's more things we can do. So routing is not the only thing, the only kind of solution to this problem. And in particular, More general protocols need not only have nodes store and forward messages, but they can even allow nodes to send arbitrary functions of messages they receive. So internal nodes in the network can encode and decode messages. Therefore, we refer to these more general protocols as network coding protocols. Okay, so what do such protocols look like? So pictorially, it looks something like this. If we think about this subnetwork. So say in a particular round, U1 and U2 might send a message to V. In the subsequent round, U3 might send another message to V. And then in the next round, U might send some function of these three messages to its neighbor W. This message can be one of these messages. This function could be one of the messages, as in routing protocols. It could be the max of these messages. It could be the sum of some of these, of course, mod 2. It could be anything really. Okay, so we're allowing for a richer solution space. Does this gain us anything? And in particular, does network coding allow us to solve multiple unicasts faster than routing? And the answer to this question is yes. So let me show you using a very simple network referred to as the butterfly network in the literature for obvious reasons. And what I'm going to show you here is that routing time on this instance is at least 4 rounds, whereas coding allows to solve it strictly faster in 3 rounds or less. Okay, so let's see that routing takes a while and consider the blue source sink pair. Notice that there's exactly one path of length less than 4 between these two using the edge UV, and similarly for the red pair. Now, if we try to route along both of these paths simultaneously, we run into the familiar bottleneck, the familiar bandwidth bottleneck or congestion bottleneck. Remember, we can only send 1 bit per round along each edge. And so if you want to solve this problem using routing, the red flow or the blue flow will either have to take a longer path, or alternatively, one of them will have to wait in the node U, resulting in completion time of 4 rounds. Okay, and now I suggest you maybe stop the video for a minute and try and convince yourselves that coding time of this instance is at most 3. So using network coding, you can solve this instance in 3 rounds. All right, hopefully welcome back from the break. So how are we going to solve this instance using network coding in 3 rounds? So first, notice that in 3 rounds, we can send the wrong message to each to each sink. So we can send the blue message to the red sink and vice versa. And in addition, in 3 rounds, we can send a combination of both of these messages. So we'll send X1 and X2 to you, combine these 2 messages. As we know, red and blue make purple. And in the 3rd round, send this combination to both of the sinks. So what this looks like in 3 rounds is as follows: 1, 2, and 3. And so in 3 rounds, both sinks receive the sum of the messages and the opposite colored message. Subtracting one from the other, they get the answer. So on this instance, network coding is strictly faster than routing. And this begs the question, how much faster can coding be than routing? So a little more formally, for any k unicast instance M, we're going to denote by TR of M the time of the fastest routing protocol for M. And similarly, we'll denote by TC of M the time of the fastest coding protocol for M. And finally, we'll refer to the ratio of these two, which is, of course, greater than or equal to 1. We'll refer to as the completion time coding gap of M. So this is how much faster coding is than routing on this instance. And our question here will be, how large can the completion time coding gap be? We know it's strictly greater than 1. There are some gains to be obtained by coding. How big can these gains be? So this brings us to our results. Our first theorem is that the completion time coding gap for any k unicast instance is at most polylogarithmic in the number of sessions. In particular, it's at most log squared k. So the way you should be parsing this is that while network coding can speed up the time to solve multiple unicasts, it can only help you so much. On the other hand, we show that this polylogarithmic dependence on k is inherent, as there exist infinite families of k unicast instances with completion time coding gap, which is polylogarithmic in k. So what this is saying is that network coding can even speed you up by a super constant amount. All right, so these are the results. Let me tell you kind of what you can expect for the remainder of this talk. So remember that what we want to show here is upper and lower bounds on the ratio of the fastest completion time of either routing or coding protocols. This requires an upper bound for one of these fastest possible completion times and a lower bound for the other. As it turns out, giving upper bounds for these is simple. You just need to give me a protocol and convince me it terminates in no more than k rounds, or sorry, t rounds. Giving lower bounds for completion time of protocols, of any protocol, is significantly more involved, and I'll therefore spend most of the talk talking about how you can improve a lower bound on the completion time of the fastest routing or the fastest coding protocol. Okay, and with that, let's start. Let's start with the kind of easy warm-up bounds. If we have a source sink pair whose distance is some d, well, that means that the time to solve this instance is at least d, because we actually need to send this information at least d hops. Now, how good is this bound? Well, unfortunately, sometimes it's pretty lousy because it misses the congestion aspect of the problem. So in particular on this network, all the source sink pairs are distance 3, but since all of these have to send their information one way or another along the edge UV, there's k bits we want to send along one edge, so this problem requires at least k steps. On the other hand, if we consider only congestion, no need to parse what's written here, let me show you a picture instead. The congestion bound says that for any cut UU bar, if we've separated, say, 5 pairs, and there's only 2 edges crossing this, well, we want to transmit 5 bits of information over a channel of capacity 2, so this will take us at least 3 steps. Unfortunately, of course, the congestion bound is not great either, as it's missing the exact opposite side of the coin, which is the distance aspect. So if we think about a path graph with S1 and T1 on either extremity, well, the congestion bound will only show us a bound of 1, whereas by the distance bound, this will take at least n steps to solve, or n minus 1. So what we really want here is a bound which captures both congestion and distance. And to kind of build motivation here, or intuition, I'd point out that one way to think about congestion bounds is that there's a small number of edges whose removal will disconnect the graph, and in particular will increase the SI-TI distances to be infinite. So a natural approach to maybe refine this bound is to maybe say, hey, what happens if a small number of edges is removed, and that causes the distances to only increase a lot? Maybe not to infinity, but increase to something. That's exactly our first bound. We refer to this as cut bound number 1. And it says that the following: if after deleting a set of f edges, marked here, all the SI-TI distances increase to be at least t, then the routing time for this instance is at least the minimum of t and k over f. And the proof here is maybe a 2-liner, so let me walk you through it. So if you can route this instance in less than t rounds, that means you have to send these k messages along k paths of length less than t. But recall that all the SI-TI paths of length less than t have to go through these cut edges. And so what this means is that there's k bits of information that will have to be sent along f edges. And so by pigeonhole principle, one of these has k over f bits going through it. And by the congestion constraint, this means this instance will require at least k over f rounds to solve using routing. Okay, so we have some non-trivial bound. Notice that I claim that this bound only holds for routing, and let me convince you of this fact. So what I'm going to show you is that this bound does not hold for network coding solutions. Well, let's consider this 5 unicast instance. Here, all the sources have an edge to U, which has an edge to V, which has an edge to all the sinks. And in addition, every SI has a path of length 3 to all the other TJs. Okay, so again, the dark edges are paths of length 3. So here, notice that if we delete the edge UV, then all the SI-TI distances increase to 5. It could maybe take 3 hops to go from, say, SI to TJ, then to V, and then to TI, but we cannot find any shorter path. So by the cut bound from the previous slides, we find that the routing time for this instance is at least 5. On the other hand, if you think about this for a little bit, this instance is just a generalization of the butterfly network. And in particular, generalizing the protocol from a few slides ago, we find the network coding protocol, which completes this instance in 3 rounds. And the way this works is every SI will send their message to every TJ. And in addition, we'll send all the messages from the sources to you, who will then add these together, send it to V, who will then send the sum to all the TJs, to all the Ts. Subtracting that from the irrelevant messages, every sink can compute its message. So what's going on here? Even though the removal of few edges increases the distance from every SI to every TI, the fact that there still remain short SI-TJ paths mean that they can somehow combine their strength and solve this instance faster than routing. So the natural strengthening of this bound to make it also applicable to coding is to require that all the SI-TJ distances increase. That's exactly what we do in cutbound 2. So the claim is if after deleting a small number of edges, all the SI-TJ distances increase to be at least T, then the coding time for this instance is at least the minimum of T and K over F. And the proof is again somewhat simple, even though I don't have a nice picture for it. So here's the observation. If you can solve this problem with coding in T rounds or less, then this means you're sending K bits of information from the union of the SIs to the union of the TJs. But since all the SIs and all the TJs are at distance at least T, if you solve this in less than T rounds, all these K bits have to go through the edges in F. And so again, by pigeonhole principle, some edge in F has a large number of bits going through it. And so by congestion, we're done. All right, so we have 2 bounds to lower bounds completion times. Let's try and get a sense of how good they are. So let's consider the family of graphs, which is widely studied in the distributed computing literature. So here we have root n paths of length root n. And the first and last node on each of these will be the source and the sink of some unicast session. And in addition, in each of these paths, the ith node neighbors the ith leaf of a complete binary tree. Okay, so why should you care about this network? Well, this network has been used in the distributed literature to prove unconditional root n lower bounds, despite this network having a low diameter. And kind of following the same rationale that gives us lower bounds in the distributed setting, we can show that the completion time for this instance is at least root n. Now, the warm-up bounds we saw at the beginning of this, the technical part of the talk, is at most logarithmic. The distance and the congestion bounds will only show us a log n bound, or worse, or lower, sorry. On the other hand, our cut bound number 1 can be used to show a 4th root of n lower bound, so exponentially better than the naive warm-up bounds. Unfortunately, this is still polynomially far from the right answer. And since we're interested in giving polylogarithmic upper and lower bounds on the completion time coding gap, we need to have much tighter bounds on the completion time for every instance. So what we need here is a better bound still. Now, to build intuition for the stronger bound, notice that in cut bound 2, we were saying if you remove a small number of edges, then the distances increase to a lot. So what does it mean to remove an edge? Well, essentially it means we've increased its length to be either infinite or maybe at least T. So it's not relevant for short transmission. So what happens if we extend edge length to be something, in the middle between 1 and infinity? And that's exactly what we do in our final lower bound, which we refer to as the moving cut for reasons which will hopefully be clear in a few slides. So we say that if after increasing every edge's length to some positive integer LE, all the SI-TJ distances are greater than T. And in addition, the sum of length increases is small compared to K. In particular, sum over E, LE minus 1 is less than K. Then the coding completion time for the instance M is at least T. So I'll prove this in the next slide, but let me just point out a few small things. First, this cut captures the previous 2 bounds, if we set the lengths appropriately. And in addition, this actually gets the right bound for the instance of the previous slide. Even better, it gets the right bound across the board. ignoring polylog terms. Great, so we're almost there, so let's see why this bound is true. So let's look at our network, and let's group the vertices by their L distance from the set of sources. So pictorially, it looks something like this. So we have level 0 as sources, level 1, etc., etc. And notice that by the moving cut definition, all the sinks are in levels T or higher. Okay, so let's start with a warm-up. Imagine all the edge lengths are 1, so we didn't increase the length of anything. Well, in that case, the information is restricted to, after D rounds, the information is restricted to all the nodes at distance D or less from you. So in round 0, only the sources know anything related to the messages. In round 1, only the sources and their neighbors know something, and so on and so forth. And since we know that all the sinks are at distance greater than T, if we just try and send the information somehow in T-1 rounds or less, this information will never reach the sinks. Okay, let's see what happens when the edge lengths are a little more general than that. So here what we claim is the following. If you consider an edge E of length LE, then we can only send at most its edge length increase, so LE-1 bits ahead of this wave of information. So for example, consider the edge UV here. So first notice that its length is at least 3. Otherwise, V would be in an earlier lower level. And what we're going to see is how many rounds you can send a message to V before the wave reaches V, in which case we imagine V already knows all the messages. So between round 0 and round 1, U doesn't know anything, so of course it cannot send a message. Between round 1 and 2, same thing. But now between round 2 and 3, U has already been hit by the wave. What's going on with the animations? And so it can send a message to V. So that's 1 bit. Between round 3 and 4, it can send another message. That's 2 bits. But now in the next round, V will have already been hit by the wave, in which case there's no more information that you can send, which will go ahead of the wave. Great. So now summing up overall the edges, what we find is that the number of bits that are ever sent ahead of the wave, and therefore have some chance of reaching the source, the sinks in T rounds or less, in less than T rounds, is at most the sum of the edge length increases, which by the definition of the moving cut is strictly less than K. And so what we find is that at most, strictly less than K bits reach the set of sinks in less than T rounds, and therefore the completion time for this instance is at least T. Great. So now I've given you kind of the crux of maybe the core of what's going on in this paper, albeit at a somewhat high level. Let me try and show you how you can use this to prove upper bounds on the coding gap. Of course, this is going to be a somewhat high level view. Okay, so as a reminder, our main theorem is that the completion time coding gap for any K unicast instance is at most polylogarithmic in K. And the way we prove this is as follows. So first, we study a linear programming relaxation of what it means to route this instance M in T rounds or less. And our first observation is that if the optimum value of this LP is at least some constant, then there exists a routing protocol which solves this instance in time T. And this builds on somewhat standard tools, the congestion plus dilation framework of Leighton Mags Rao and randomized rounding approach of Srinivasan and Till. The crux of the analysis here is in showing what happens in the opposite case. So if the optimum value of this LP is small, we show that not only is the fastest routing actually pretty slow, but even the fastest coding protocol is actually pretty slow. And in particular, the fastest coding time for this instance is at least T over polylog K. And here the key insight is that if the optimum value of this LP is low, then by strong LP duality, there exists a dual solution of low value. And what we show is that a low value dual solution allows us to construct a moving cut with which we can prove a lower bound on the coding time. Okay, so these are kind of the key ingredients, just to kind of satisfy you that we've seen enough to prove this theorem. By point 2, we find that T star, if we take T star to be the coding time times some polylog term, then the optimum value of the LP with parameter T star is at least 0.1. because otherwise by point 2, we'd have that the coding time is at least t star over pi log, which would mean that the completion time TCM is strictly greater than TCM, which is just not how numbers work. Okay, and then combining this with point 1, we find that the routing time for this instance is at most t star, which is the coding time times some pi log term. And with that, we're done. All right, let me skip the lower bound proof, which is even more high level than the upper bound proof. And let me conclude with a summary and a discussion of intriguing open questions. So first, I'll recall that the main theorem of this work can be stated succinctly as follows. The completion time coding gap for k unicast instances is at most pi logarithmic in k for any instance, and can be pi logarithmic in k for some instances. Some extensions studying this work, which we didn't address in this talk. In this talk, we assume that each edge can only send 1 bit per round. We can generalize this to general capacities per edge. We also assume that the time to cross an edge is exactly 1 round. We can generalize this to arbitrary delays for each edge. And in the talk, we only focused on maximum completion time. We can also address average completion times and other functions of the individual completion times. And for all of these generalizations and extensions, we get the same bounds as in the main theorem above. Finally, in this talk, we also assume that all the message sizes are 1 bit each. We can also generalize this to arbitrary message sizes. And this captures the well-studied throughput maximization problem, which is the special case of infinite-sized messages. And for this generalization, we achieve essentially the same upper bound, a polylogarithmic bound in the network parameters, in the problem parameters. All right, some intriguing open questions. Well, the most obvious one, just looking at the theorem from the previous slide, is figuring out the right completion time coding gap. We know it's some pi log, but what pi log? Next, since we showed that network coding can speed up the time to solve multiple unicasts by a super constant factor, and since we know how to compute the optimal routing protocols, the natural question is, can we compute the optimal coding protocols? Finally, let me point out another, maybe not apparent, open question from the talk. As I mentioned in the previous slide, the problem we study here generalizes throughput maximization. Those of you in the know that studying coding gaps for throughput maximization has proven to have surprising relations to other areas of TCS. And so what I'll ask here is, does our work, or the problem studied in it, have similar surprising connections with other areas of theoretical computer science? And well, I guess we already have an answer for this question. The answer is yes. And in unpublished joint work, we use our coding gap upper bounds from this work to obtain universally optimal distributed algorithms for a number of fundamental problems. And here by universally optimal, I mean that these algorithms are optimal on a graph by graph basis. So if you give me your graph, I'll give you the fastest algorithm for this particular graph. This should be contrasted with worst case optimality, where you have a bound saying this algorithm will complete in t of n rounds, and there exists some pathological input on which t of n rounds are necessary. Okay, so going back to question 3, apparently there are connections between these network coding questions and other areas of TCS. So let me refine this question and ask whether or not there exist more such connections with other areas of theory. And with that, I'll thank you for your time and hopefully see you in Fox 2021.